Third form, this little experiment looks at how you can take the reactivity of the metals and actually use that to predict whether or not a reaction will take place. So you all did, and some of you did amazing posters on the reactivity series of metals. So you can see here on page 14 that you've got some mixtures, and we're going to react these mixtures together and see what happens. So our first mixture is iron and copper oxide, and what that really means is the copper is bonded chemically to oxide, really oxygen, the element oxygen. So they're bonded together, and the iron is going to try and steal that oxygen away from copper. And the way you can predict whether that will happen or not is if iron is higher up in that reactivity series compared to copper. So if you think of your sentence that you made, does the letter I in the sentence come before the letter C representing copper? So you have a wee think about that and see whether or not you think a reaction would take place. And so while you're having a wee think about that, I just want to talk through this setup. This is a diagram that you did take down into your unit. And I have the Bunsen lit here, and it's on the safety flame at the minute. I'm about to change it to the hot flame. But what's important about this setup is I have a test tube. Here, I have a little bit of my substance. This is the mixture of iron and copper oxide at the bottom here. It's clamped into it's clamped onto the clamp up the top here. So the clamp is clamping around near the top, not anywhere near where we're going to heat it. And also it's angled. It's not being heated directly from below. It's being heated at an angle. And that test tube isn't pointing anywhere near anybody. Obviously there's not very many people in school at the minute, but if you were doing this as a class practical, you would have to make sure that the test tube wasn't pointing anywhere near anybody. So I'm going to make this Bunsen burner really hot and give this some energy to help it to react. And we're going to see if iron is able to pull away the oxygen from the copper. Now what I really want you to keep a wee eye out for is any evidence of any reaction taking place, and that might be something like a red glow that you would maybe see in the test tube where a reaction is taking place. So you might notice that it's kind of moving a wee bit. That's probably just because there's a wee bit of air, and that air is expanding, and that's making the powder jump up the tube a little bit. That's all that is. It's not actually a chemical reaction just yet. But we'll know when it happens because it will start to glow. Now, in the documents that we've posted online for you, you can see the observations that you're supposed to get with this, but we really wanted to let you see it happening for real. And sometimes it takes a wee while to get it hot enough. Reactions need energy to help them to start. And then once they start, as this is just about to start, I can see now, once they start, they tend to heat themselves. Now, I can see at the very bottom of this test tube there is a red glow. And so the reaction will happen if I just keep reacting that. So it is glowing red hot at the bottom. So I just keep heating there. And it's really beginning to glow red hot now. And that's evidence that that's more heat than's coming from the Bunsen. That's energy from the reaction. And that's because the iron is stealing the oxygen away from the copper. And at the end of this reaction, we should be left behind with copper and on its own. So copper's a red-brown metal, and iron oxide, which is kind of a red-brown powdery solid. So in your notes it says the black-grey mixture glows red hot, and uncooling a red-brown solid is observed. So you can definitely see that red hot glow there, which is showing that the chemical reaction is taking place. You may be able to see as well that I'm actually lifting the Bunsen. If you were doing this as a class practical, we wouldn't advise you to lift it. But I'm just trying to get it to get as hot as it possibly can. What I could do is lower the clamp, but I've decided I want to sort of target the heat of the Bunsen. So I hope that you can see that that redness that's at the bottom of the tube isn't just coming from the Bunsen, it's coming from the reaction itself taking place. So if I just keep heating this for a wee moment. So third form, hopefully you saw in that first test tube some wee red-brown flecks of copper, and that was because the iron was able to steal the oxygen from the copper because it's more reactive than the copper. So this next mixture that I've got is iron oxide and copper together. So you can see it's a different colour this time because the copper's a red-brown metal and the iron oxide's a reddish-brown powder as well. So this time the oxygen is bonded to the iron and the copper's going to try and steal. And so what you may be thinking is that this will not happen because copper is less reactive than iron. So copper will not be able to steal away the oxygen from the iron. The iron's going to hold on to its oxygen and the copper isn't reactive enough to steal it. So if I give this a good heat, and we'll just try and prove that. So we think that there would be no reaction here. This is really the reverse. If you look at the chemicals, this is really the reverse of the first reaction. First reaction was the iron was on its own and it wanted oxygen, so it tried to steal it from copper. This one, the iron's got oxygen and the copper's trying to steal it from the iron. So you can see it's darkening a wee bit. And you know that's just because the copper's actually reacting with oxygen in the air. You don't really need to know that, but that's what's going on. Copper oxide forming, but the copper's trying to steal from the iron and it can't do it because it's not reactive enough. It is glowing red hot at the bottom, again from the heat of the Bunsen, but it's not glowing as much as the first one because there's no chemical reaction taking place. So I'm going to pause with this now because all that's happened is the mixture has darkened slightly because the copper powder in there has reacted a little bit with the air, but it wasn't reactive enough to steal away the oxygen from the iron. So girls, the third mixture that we have is zinc and iron oxide. So now the competition is between zinc and iron, and the iron's got the oxygen and the zinc wants it. And so again, if you think of your reactivity series, zinc is above iron, and so it's only just above iron though, so we should see a reaction here. So again, I'm going to heat this and we're going to see what happens. You'll notice in your observations there are quite a number of things that we should see here, and we're going to try and explain where all those observations come from. You may not be able to see that this is a silver and red mixture. The silver would be the zinc powder, and the red mixture is the iron oxide, but we've mixed it up, so it probably just looks to you like it's a red mixture, but there are zinc particles in here. So let's give it a warm and see what happens whenever this reaction takes place. Remember, the zinc in there is on its own and it's after oxygen, and it's going to try and steal that oxygen away from the iron if it can. And we predict that it should be able to do that because it is more reactive. You might notice a wee bit of condensation on the tube. That is just from the air in the tube. It's not anything to do with the reaction. Just when you heat something, sometimes you get little bits of condensation forming. Could be that the test tube maybe was cold. This is now darkening. So I'll just keep heating it. Get it really hot. You might have noticed that when the test tubes were finished heating, I didn't put them back in the test tube rack. And the reason for that is they're really, really hot. And so I've set them down on a heat-proof mat. Just taking that away a wee moment, I can sort of see what it's trying its best to react. I put them on a heat-proof mat because if I'd put them in the test tube rack, they would have melted the paint on the test tube rack. So anytime you're heating something, you never put it, you always think carefully about where you put it afterwards. A little bit like if you're doing some cooking at home, when you wouldn't take a hot pan and just put it onto maybe a plastic surface because it would melt it. And obviously with all of these things we're being really careful that we don't touch the hot apparatus as well. We make sure it's completely cool before we touch it. Now you will notice that this is a wee bit slow to react. It's certainly slower than the iron oxide and the iron and the copper oxide. The first one is slower than that. And when you get reactivity series, it's not just that it's above the element in the reactivity series, it's how far above it is as well, determines how fast it will react. So these two are pretty close. This is like Premier League game between two teams that maybe are really similar in ability. The zinc and the iron are competing strongly in there for that oxygen, and the zinc is just about winning. It's beginning to glow red hot now. We can see now that that is beginning to react. I'm just taking the heat away, and I hope that you can see there's a yellow solid forming near the top. You might be able to see that, you might not. Just going to take the heat away, because when a chemical reaction starts, it creates its own heat often, and that keeps heating things up. Here's something really interesting about zinc when it bonds to oxygen that I think is really clever. When zinc bonds to oxygen, it makes zinc oxide. But zinc oxide, when it's hot, is yellow. So when it's hot, it's yellow, and you can maybe see that on the side of the test tube, that when it's hot, that zinc oxide is formed. And then when we let this cool, when the zinc oxide cools down again, it goes white. But I'm going to take this out of the clamp in the moment. It is going to be really hot, and I'm going to set it on the heatproof mat. But what we've got now, and I can clearly see it. I know Mrs. Shaw's going to zoom in and take a wee photo for you, let you see. But at the bottom of that test tube, there's very clearly a silvery colour, and that is iron. So the iron has lost its oxygen, and it's changed into pure iron, and the zinc has gained the oxygen, and that's what the yellow colour is, which is losing its yellowness as I chat to you there. But it took a while for that to happen, and that's because zinc and iron are really close in the reactivity series. In your unit it says silver and red mixture glows red hot, shower of sparks. Sometimes if the iron oxide gets lit, it can be sparky, it can make like sparklers, but it didn't in that case. But sometimes that's why that's in there. Yellow solid seen on the side of the tube, but on cooling the yellow solid turns white and there's a grey solid at the bottom. So we've got all of that happening, and I'll put it onto the heatproof mat nice and carefully now, and then we'll get a wee photograph of that. So the third form, the last mixture, is zinc and copper oxide, and we've moved to the fume cupboard for a reason. So this one, if we think about what might happen with this one, so I said earlier that it's not just that one metal is more reactive than the other, it's how far apart they are in the reactivity series. So zinc is in there, zinc is like a grey solid, and zinc is in there, and it's going to battle with copper for oxygen. At the minute the oxygen's bonded to the copper, but the zinc wants it, and so it's going to fight copper for it. And because they are very different in reactivity, zinc is much more reactive than copper. This is if you were doing this in class, this would be a teacher demo, so that might give you a clue as to what might happen. So again, I've got my Bunsen burner ready, and I'm going to change the flame to make it nice and hot, and I'm going to heat it, and we're going to see what happens. So again, with chemistry, often reactions need energy to help them start. But then once they start, they create their own energy. And then that's what can cause reactions to go very, very vigorously and quickly. Again, you'll notice that we've angled this test tube to face the screen, glass screen. We're not pointing it at anybody. Beginning to glow red hot. Now you might have seen my hand jump there. I'm laughing because we wondered what else might happen. In fact, you know what's happened there? I'm going to turn the gas off, because this has created so much heat that it's actually melted the glass of the test tube. I'm glad it didn't melt it completely and that whole all that mass sort of fall on my skin. So that was extremely vigorous, that reaction. And maybe whenever you're watching this, you might want to watch it again to see it go, because when we heat substances, when a reaction starts, it generates its own heat, and that heat from that reaction was enough to almost melt that test tube. So you can imagine how hot that was, and how we then have to respect our chemistry whenever we're doing it. and understand. So I kind of knew that was going to happen. I knew it was going to give out a lot of energy, and the reason why I knew that was because zinc and copper are very different in reactivities. Zinc is very much more reactive than copper. So we hope you enjoyed that little demo of those different reactivities of metals. So therefore, what I would like to show you is what's inside this test tube, because I do think we've made quite a wee bit of copper. So I tipped out the contents of the test tube onto the heat-proof mat, but you can see just to the right of the test tube, not very much came out. And there are little bits of copper in there, but it would be hard for you to see that. Now, we wouldn't normally do what I'm about to do at all, but because we can't use this test tube again, we are going to break it safely. So I'm going to break it safely. I'm going to put it in a wee bag and hit it with that gently with a hammer, and we're going to break it safely and see if we can find out what's inside. Now, obviously, this is not something we would normally do, but I say just so that we can do it safely and let you see, because we think again, science is all about predicting. We think that there must be copper in there, and there's also zinc oxide, which is a white powder, but the copper you can maybe see right at the very bottom. I think that's pure copper, and I'm going to try and get that out. The test tube actually cracked as I was moving it. That's why you always have to be careful when you're doing chemistry, because it was heated so much. It actually cracked and was, but still safe enough. We put it in a wee plastic bag, and I gently tapped it with a hammer. I didn't smash it. I tapped it, and I hope that you can see that there's definitely like a red-brown solid on top of that, on top of the mixture, and that's our pure copper. But I hope in this reaction you can see that not just the zinc didn't just react with the copper, it reacted really vigorously because it's quite far above the copper in the reactivity series.